What was regret? What do we mean by regret? Not everybody at once. Someone bail me out. What's regret? Not Steven.
Average difference between loss of your policy with the best expert.
I would typically call regret just the sum rather than the average. So I'm going to turn that into math, right? I'm going to say sum equals the loss of our algorithm, whatever our algorithm is, minus loss T of the best expert in our class of experts. Okay. And then we'll typically care about average regret, right? And so what is the maybe surprising thing that's true about average regret? There are algorithms that do what? This algorithm. Lightweight majority. Instead of what property?
You can bound the regret by a constant with respect to T. Or wait, log T.
I'm sorry.
Log T. Wait, log T or square root of T.
Good. So it'll at least be, we call this the regret, as 1 over T of regret will go to 0 for large T. Okay, so the average regret will go to 0. In particular, there exist algorithms that have the property that the regret, not the average regret now, is on the order of square root. Okay. It turns out under special conditions, there actually are ones that are log T, but that requires special conditions of loss functions. This is actually the best you can do in the general case. Okay. Before we get into convexity again, and then information theory, I feel like I'm covering like all the math of computer science in like 2 lectures. Let's look at an example of we talked briefly about an example that was kind of a portfolio optimization example. Let's look at another example, just because I think it's somewhat informative, of linear classifiers. Okay, just get some idea. And Stephen will probably cover some version of this later better, but I think we can get the first idea. So what are linear classifiers? What does it mean to be a linear classifier? I'll fill in some more details and you can help me out. So imagine I have some features X. So, points. Okay, those are some X's. X1, X2. Okay, what's a linear classifier for those kind of features?
If AX must be greater than 0.
Yeah, that's right. I'm gonna make it linear, not affine. The thing you just said was affine. Just to make it easy, I'm gonna make it linear. And so for these two, I'm gonna make it theta transpose X. Okay, for some set of parameters, theta. In this case, it's just 2 of them, right? 1 for X1, 1 for X2. Okay, and I'm gonna say a linear classifier has a property that if theta t X is greater than or equal to 0, then the classifier outputs 1. And if theta t X is less than 0, then the classifier outputs, say, -1, 0, whatever you want the other thing to be. Okay, this is a binary linear classifier. Okay, so a question you might ask is, Imagine I wanted to learn a linear classifier. You guys almost certainly know ways to learn linear classifiers. But let's just ask the kind of basic information theoretic argument of how hard is it to learn a good linear classifier. Okay. In particular, what I'm going to want to do is I'm going to want to do nearly as well as the best theta. So the problem you're imagining is some set of features are generated. You're forced to make a prediction, okay, using those features. What you really should think is that you're really producing a theta, and that the theta transpose x is computed from that theta, and that gives you predictions. Okay. How might we use the multiplicative weights idea to be competitive with the best data? And I'm going to be very sloppy. Stephen will be unsloppy and show you how to do it exactly later. But I want to give you the idea. What I would be interested in knowing is how important are the number of dimensions, the number of features, x, in how hard it is to learn a linear classifier. That's the thing that I'm going to try to figure out. Okay, so what is the most brute force way I might approach this?
Write down all theta.
Okay.
Try
good.
them all.
Okay, good. I'm going to try all things. So there's 2 dimensions of theta. One, there are 2 that match when I do the transpose x. Okay. If you think about it, the scale of thetas don't actually really matter, right? Because all that's really going to matter is actually the direction of the theta as to whether it's going to be greater than x. Meaning if I have a theta, so the theta transpose x is like 0.1, if I multiply that theta by 10, I will get something which is 1, which will still be greater than 0, which will be 1. Does that make sense? So the actual scale doesn't matter. In fact, all that really matters is points on the circle. I'm going to be super lazy and ignore that, because I'm going to upper bound that by saying I'm going to consider all the thetas, let's say inside the circle or inside a box, even more lazily. Okay. And I'm going to grid it up because I'm really lazy. Okay. So I'm not going to compete against all thetas right now. I'm going to compete against thetas which are like a discretized version of the thetas. Okay. How many thetas do I have?
Infinite number of thetas.
I'm going to discretize though. You were right, I have an infinite number of thetas. Okay.
To whatever degree you quantize the space.
Okay, good. Let's say that I make the spacing so that there are in one dimension b points.
B squared. Or
In general,
yeah,
b to the
B to the third.
b to the number of dimensions. So b squared because there's 2 dimensions here, right? But I'm actually going to have a number of experts, which is b to the d. Okay, I'm being sloppy again because really there's something like a d minus 1 really going on because actually all that matters is the shell. The inside doesn't actually matter. They're all, because basically any point that's along this line is going to get the same classification. Okay, good. So if I run my weighted majority with these guys as my experts, each point in here, that's one of my experts. And I'm trying now to compete with the best of these kind of discretized set of linear classifiers. What is my regrets dependence on the number of features? Remind me of the dependence in weighted majority of the regret on the number of experts. Logarithmic, right? And the thing that you're thinking in your head is you're thinking of that halving algorithm we talked about to begin with, where in the easy case, there's some expert that always gets the answer right, right? And then I can half the number of experts with every mistake I make. Okay, so we know the dependence of something like weighted majorities, regret, is like log n in the number of experts, which means the regret for learning a linear classifier is what's its dependence on dimension? This is our number of experts, right? So it,
linear in number of dimensions.
yeah, so our regret for learning a linear classifier is like b log b, where b is our number in each dimension. Okay, this turns out to be true. So if you're learning linear classifiers, even though this is a handling of the argument because I did the discretization, you can get rid of the discretization and do it in continuous space. We need to assume convexity later to do that, which is going to do the trick. But it really is true that in general, if you want to compete with the best linear classifier, you're going to need order d number of samples. Okay? So there's an insight about classifiers that you can get just by looking at the number of analyses. Okay. You'll notice this is a wildly inefficient algorithm. Why is this a wildly inefficient algorithm? You would not do this for reals, right? This is just telling you what the dependence should be. Why would you not do this for reals? Why would you not learn a linear classifier this way?
It takes too many markers to write down all the half spaces.
There's a lot of these dots, right? And when I run my weighted majority, I have to keep a weight on each of those dots, right? And there are like exponential in the number of dimension dots that I have to keep track of weights on, right? So to run this algorithm, I'm doing a exponential in d amount of computational work, right? But my regret is only linear, right? So it's computationally not efficient, but it is statistically in this adversarial classification setting efficient, right? It only takes polynomial, in fact linear, in the number of dimensions to learn an optimal classifier. Okay. So that's kind of neat. Just another example of no regret. You'll see more of it as we go along. Good. Now we wanted to transition to information theory with a little detour through convexity because we're going to need it in the information theory discussion, and then we're going to need it again when we start solving games. Which we're going to do a lot of game solving. Okay, so that was first. Statistical algorithms are going to be game solving algorithms. So we talked about convexity. Convexity is, when we talk about sets, it's just that every point can see every other point, or if you draw a line between 2 points in the set, that also lies inside the set. It means convexity. Okay, we talked about convex functions. So convex functions are functions for which, if you look at the area above the function, it's also a convex set. Okay, what if you consider, and so this is going to be the actual definition that we care about, is what if I consider points that lie along the function itself? What's true about the function and the line between those points?
The line is above the function.
The line's above the function. Okay. So if we put that in math, what does that say? I'm going to have alpha 1 and alpha 2 that are greater than or equal to 0. And sum over I, alpha I, so 2 of them equals 1. Okay. I'm going to use this to make the line. Okay. Then what's true? If I look at sum over I, only 2 of them, alpha I, f of xi, so this is x1, this is x2, right? This is f of x1, this is f of x2. What is true for this? This is what?
Greater or equal to f sum of alpha xi.
Yeah. Remember, the alphas are just 2 points right now. Just being lazy and writing it as a sum. Okay. So this is literally the translation of this, which is that this point right here lies above that point right there. Okay? And that follows from this definition of the epigraph. Because what we said is that if you look at any 2 points in the epigraph, right, the line between them will be in the set, which means they must be above the set. Okay, good. That's convexity. It turns out this is a more general phenomenon. And meaning I'm going to be able to make this true for alphas more than just 2. Okay, so this is effectively definition. Okay, but I can generalize this definition, or I can generalize this to a theorem, and I'm going to give you, well, the theorem's kind of written on the board already. I'm going to give you the picture and convince you that it's true, and not give you an actual proof. But the proof is basically just induction on this statement. Okay. So, what if I take a single picture, point, I take 3 points, here, 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 okay. I can make a shape of these 3 points. That shape right there, which is mixing these points here, right? So these points, this point right here is x1, f of x1, right? That's its coordinates. Similarly, this is x2, f of x2. This is x3, f of x3. Okay. What is also going to be true for a convex function? This volume right here is actually just what? What are the points in here? This shape. How do I get this shape?
I forgot the name, but it's a subset of the area over the graph, which is also a convex set.
It's a convex set, but in particular, a point in here is going to look like some alpha I xi, right? It's going to look like this. Some alpha I xi. Good. And what? Some alpha I. It's going to be its coordinates. Okay. And the point is, all of these points in here are also above the function. Okay. So if I pick a point, well, like this one, it's above the function. In fact, if I pick any point in here, it's going to be above the function at the same mixture of xi's. Okay. That statement is actually just this statement with more than one alpha I. Sorry, more than 2 alpha i's. Okay. So the general version of this, where I doesn't run just from 1 to 2, when it runs from 1 to 2, it's just a definition of convexity. When it runs from 1 to n, this is called Jensen's inequality. And we might write it like this. We might write it as expectation under some distribution P of f of x is greater than or equal to f of the expectation under that same distribution of x. Okay? I probably use Jensen's inequality, I don't know, how many times per year. Every time I use it, I have to draw the picture to remember which way the inequality goes. So have no fear that you need to draw the picture, right? So you draw it yourself and just look and say, wait, okay, if the function is convex like that, then the average of points lies above the function evaluated at the average. Now, if your function is concave and looks like this, which is minus convex, then the function, the average of the function lies below the function of the average. So again, I have to check it every time. I find there's no shame in that.
Is it Jensen or Jensen?
I believe it's actually Jensen,
Okay.
but I'm not positive of that. Well,
Yeah, I think Jensen's inequality refers to the GPU gap between industry and academia.
Clever. Okay, good. So we're going to use that today. Now we're going to talk about information theory. Okay. We'll use Jensen's inequality in our discussion of information theory. So now for something completely different. I'll walk over here. Information theory. There's a theory of pressing information, sending information, and probabilities in general. Okay, let's say I've got a variable, call it x, that I'm uncertain about. Okay, so it could be that it could be a letter in the alphabet. Okay? I'm not sure what the letter is going to be. So I've got some degree of uncertainty about this thing. And I want to write it down in the most compact form I can on average. That's going to be what the goal is, okay? Is that I can write down the description of what value that variable takes on in such a way that on average, my number of bits required to write it down is as small as I can get. Okay? I don't want to encode something in arbitrary way, I want to encode it efficiently. That's the goal. So it's all about encoding things efficiently. Okay, so let's come up with a really concrete example. Let's say x can take on 4 different values. Okay, and we'll call them arbitrarily A, B, C, D. Okay, those are the 4 values that the variable can take on. And I'm going to tell you that my probability or belief that A is going to take on, x is going to take on the value of A. So this is x equals A is 1/2. That's the probability of that happening. The probability of B happening is like 1/4. Okay. The probability of C or D happening is going to be 1/8 each. If I did that right, those add up to 1. Okay. If I did that wrong, things may go off the rails at this point. Okay. So I'm going to invent a code that I claim is optimal for this problem, which is I'm going to say, I'm going to use bits. I'm going to only use 0s or 1s just to make it easy. Anything to encode this, but I'm going to use the simplest thing we can think of, 0s or 1s. I'm going to code A, if A appears, by the number 0. Okay. I'm going to code B as 1, 0. Okay. I'm going to code C and D as 1, 1, 0, 1, 1, 1. Okay. Does that make sense? Seem like a reasonable code for this thing. Why did I choose it this way? Why did I choose this code?
The less probable, sorry,
Go for it.
the less probable bits, the less probable values get higher number of bits.
They do, right. So,
Bigger space.
and that's good because I would much rather, if I want to be good on average, right, I would much rather that the frequent things have short descriptions. Okay, this is true in languages actually, very, very, very crudely, is that things that are more commonly said tend to be shorter, right? Because it's more efficient encoding. Okay, you can get information across more quickly. Okay, it also, it has a unique decodability property, right? So it has the trivial unique decodability property of that, well, I didn't assign 2 codes to the same thing, because that would be embarrassing, and then I wouldn't be able to tell you what the actual message was. Okay. It also has a property which we won't spend much time talking about, but turns out to be important, which is it's called instantaneously decodable, in the sense that I immediately know in this code when the message is done. Okay. So I don't have to like wait to the end and then be like, oh, that was a code word. Okay. And in fact, I can actually append these together. Right. So let's say my message was AA. Right? I could append this as 0, 0 and never be confused that that's one of these other codes. Okay, so that's one other reason why I picked that particular code. Okay.
Good, so we chose it so that it's longer. So what's the length of, for any particular message, what's the length of the code in terms of the probability? I picked it carefully, hopefully. How long is the first code? First code is? How many bits? How many bits is the first letter?
1.
Good. Second letter? 2. Third letter? 3. Okay. You notice a relationship between that and the probabilities?
The expected number of bits is roughly the same for each entry, or close to half.
It's the exponent,
I think you're getting fancier than we are quite yet. We'll come to that in a moment. Go ahead.
I mean, the ratio of the length is basically the ratio, I mean, C is basically a half to the power of 3, and that is the ratio of the length.
1 over 2 to the power n, with n the number.
Yep. So I think this is the same thing you're saying, right? But it's basically log base 2 of, I'm going to, by the way, write down ln a whole bunch when I actually mean log base 2 because I use ln a lot. So just keep an eye out for that. I probably didn't mean ln. 1 over pi. That's the actual length, right? So if I take this guy, this guy's code is log base 2 of 2, right? This guy is log base 2 of 4, which is 2. This guy is log base 2 of 8, which is 3. Okay. So this is in general going to be true that, I know there's a whole bunch of caveats to this, but let's see if I can explain the caveats. This, by the way, this is sometimes called the information content of outcome I. I can't say that I ever hear this in common use, but that's the information content of outcome I. Okay, so some outcomes have higher information than others. In particular, what are the high information content values?
The rare events.
I'm sorry?
Rare events.
The rare ones, yep. C and D in particular are the rare events, and they're the high information events. Okay, so when we use information in this word, we should almost think of it as like surprise, right? The high information things are the things that are surprising. And that might make intuitive sense. If you expected something to happen, you're not gaining a lot of information if I tell you it happened. Right? You gain a lot of information when I tell you something weird and rare happened. Okay, so that's the information content of an outcome. Okay, the thing that I want you to believe without proof is that for any set of probabilities, I could do the same kind of encoding. Okay, this seems implausible, but I have to do something to make it true. Okay, so first off, what I'd have to actually do is I'd have to code a bunch of letters at the same time. Okay, so in this case, we coded just one single X, one single letter. Okay, but now imagine that I'm going to code a whole list of letters. Okay, I could do it with this code for my A, B, C, D. If these probabilities weren't conveniently powers of 2, I could get really close with groups of them to making them really close to powers of 2. Okay, so I could code like, you know, AAA as something close to a power of 2. I could code AAAB as something close to a power of 2. If I get blocks that are big. In fact, if I make the blocks big enough, I can get it very close to being able to encode every sequence of letters by something that's close to one of these powers of 2. Okay. And then I'm going to be able to build a code that won't work for just a single letter. If I'm going to send a single letter, but if I'm going to send a block of letters, it will be very close to the information content, will be about log base 2 of 1 over pi. Okay, that's the thing I want you to take without proof. There's a good proof in that David Mackay book. There's an excellent version in Tom Cover's book. Okay, If you believe this part, so take that as a given, that I can get very close to this for any probability distribution, then what is the expected number of bits? If you see a single variable x, what is the expected number of bits that you expect to need to encode this? On average, how many bits are you going to need to encode it? What I'm expecting is a piece of math, not a number.
Is it the entropy? So pi times log 2, 1 over pi.
Okay, we're going to define this thing as the entropy. This is the Shannon entropy. Turns out that there are actually many things that get called entropy.
CMU Cafe.
There we go. Yeah. Is it the cafe or is it the place you get the food? Like the little.
It's the market.
It's a little market. Yeah.
Oh, the market.
Yeah.
I only remember it where this place to play ping pong.
Yeah, all right. So Shannon entropy, there are other notions of entropy. Von Neumann entropy is one that are not equivalent to this idea. There are a bunch that are sort of equivalent to this idea. I believe Shannon said that when he created this theory, he was talking to von Neumann about what to call this quantity. And von Neumann says, well, it looks like entropy that shows up in physics, and if you call it entropy, nobody will know what you're talking about, and you'll be fine. So no one will argue. So that is the alleged reason that it's called entropy. And so what it is some EI log, log raised 2 of 1 over pi. Okay, which is just the expectation under P of log 1 over. Okay. This is just literally the average, right? I'm literally just taking the average of the number of bits required to encode each outcome. Okay, good. So, what's going to make the entropy large?
Again, more number of elements.
Yeah, well, wait. More number of events for sure will make the entropy bigger, right? If I just have more things to encode, like more different possibilities to encode, I'm definitely going to make it bigger. That's good. What would make it really small? Let's put it the other way. Maybe the other direction's easy. How can I make the entropy really small?
You have probability events.
In fact, what's the smallest I could make it? Right. Then the entropy would be effectively 0. Okay. So good. If you think that being very, very certain about something is going to make it small, what's going to make it really big? What's that? Good. I think we'll prove this later, but uniform distribution is the maximum entropy. All events are equally surprising. Good. And so what does that mean that the entropy is bounded by? Do you believe that part? Then it's like some 1 over n log 1 over n, where n is the number of possible outcomes, right? What's that give me?
Log n.
Yep, because each of these guys, I can just pull this out, right? And then each of these, the n of these, so the n and the 1 over n are going to cancel, and this is just log n. Log base 2. Okay, so that's the biggest the entropy can be. Does that make sense? Okay, what if I build my code, say using this distribution, okay, but the messages that come to me, so you're gonna get messages that you're gonna encode, come from some other distribution, Q. So we have 2 probability distributions now. Okay, so I'm gonna code, meaning build the code according to P. But the symbols I'm going to get sent come from a different distribution, using all the X's and sums, etc. Okay, this quantity is called cross entropy. If you had to guess, what would you guess the best, well, kind of set it up this way. Well, what do you think if I tell you the symbols are going to come from P, what should I code according to?
P.
According to P, right? So it's going to be worse to use the wrong code, right, rather than the right code. Okay? And in fact, let's introduce the quantity. Sum P log P over Q. P Q. Okay. Does this look familiar? This thing, right, it's called multiple things. I think it's called relative entropy too. If you're in information theory land, but in statistics, it's called scale divergence. It's the most common phrase for it. Okay. And what is this saying? What is this? I literally just expanded this out. Well, what is it saying the scale divergence is? In words? I don't think so. Oh, wait, where? Yep, okay, good. What is this called?
Is it just cross entropy?
There we go. Cross entropy. In the order Q, E. Okay, I'll always use the first letter to be the thing which the expectation is taking into perspective. Easy to remember, the first thing that will appear will be the first letter, whether it's in scale divergence or cross entropy. Okay, cross entropy, and then what? You know this quantity too.
Entropy.
Is minus the entropy, right? Think of this as a measure of difference between two probability distributions. Okay, it has a meaning in terms of coding or information theory. What it's saying is, if the real set of things that you have to compress come from some probability distribution P, but you use a code built for Q, how suboptimal are you? Okay, so what should be true of this thing?
Greater than or equal to 0.
It better be greater than or equal to 0. That fact, so intuitively it makes sense, right? It's worse to code according to the wrong distribution than it is to code according to the right distribution. Okay. Meaning this is some kind of measure. It's not a metric, but it's some kind of measure of how different two probability distributions are. Okay. So that fact is called Gibbs inequality. After G.W. Gibbs, who is one of the founders of statistical mechanics. Okay, Gibbs inequality, we'll prove it in a second, but I want you to understand why intuitively it should be true, right? It should be, you're coding under the wrong, you're using the wrong distribution to code, you're going to pay some price for that. Intuitively, when is this thing really big?
Is it possible to have no overlap at all?
Right, okay, so then it's infinite, right? Because then what I'm saying is I build a code, okay? And I say that there's some letter, D, that never appears, 0. Okay? So, or think of it as it appears an incredibly rare fraction of the time, right? Then I'm going to use a really long code word to encode that, or basically not even have a code for that rare event. Okay, and now it actually appears in the other distribution, right? Now I'm in big trouble, right? In fact, let's say it appears often, right? Now I've got giant codes all the time, right? I'm way more inefficient than if I had just coded it with like 1/n for each of the probabilities. Okay, good. So scale divergence is really large when Q puts small probability, because Q is what I use to build the code on something. Okay, but P does put probability on it. That's really bad. Okay, does that make sense? So in general, what is scale divergence in this order? Notice this thing is asymmetric, right? What is scale divergence in this order going to tell you to do for your Q? The thing you really, really can't do is you really, really can't assign no probability to things that are going to happen, right? If there are messages that you could get, you better assign some probability to them, right? Okay, so it's going to, in general, tell you to do what? Essentially make sure you have covered. This version, by the way, is often called, well, depends on what you pick as P and Q, but it's often called, if the thing that we are controlling is Q, this is often called the forward KL divergence. Okay. And we're going to deal with both forward and reverse KL divergences in this course a whole bunch. Okay, they both show up. Most modern LLM trainings will end up using the reverse KL divergence, which does not have this property. Okay, so what if you think about it in the other order? So the reverse KL, let's get a little bit of intuition. The reverse KL is, you think of it as the same quantity, but I'm going to write it as some Q log Q over P. And Q is, again, the thing that we're going to control. P is the thing that we're not going to control. What would make the reverse KL very large?
We thought something was very common, but in reality it's not. So Q is large and P is small.
Right, so we control Q. Right. So we generate events, right? We generate symbols that P puts really long code lengths on, right? So P thinks it's really improbable, and we put mass on those things that P thinks is really improbable. Okay? You don't pay a lot for reverse KL if you put mass on places that P, let's see, if you put mass on places where P has code for, that's okay. Okay, the only really bad thing is you put mass on places that P really is really inefficient for. Okay. Good. Okay, let's do Gibbs inequality very quickly, and then let's look at some more examples of how this comes up. A whole bunch of examples of how this comes up. Gibbs inequality is straightforward application of Jensen's inequality. It's pretty straightforward application of Jensen's inequality. Okay, so let's see, we got Q over P. That's our KL divergence, right? I just put the arguments. Good. Okay. I gotta draw the picture. Hopefully I'll get all the signs right. That's roughly what log looks like. My sketch of what log looks like. Okay. What property does log have then?
Increasing.
It is. It's better than that though. Concave. Concave. Okay. of the line. Okay? So in particular, I'm going to write that as f of the expectation. In shorthand, is going to be greater than the expectation of that. Good. This is an expectation. This is a convex function, or concave function. Okay, so what can I do now? Using this idea. The expectation of a function, okay, is, I'm going to hold the minus aside for a minute. Remember that this is going to be minus b log p. We'll come back to that. This thing right here is the expectation of a function, of a concave function, which means it will be less than or equal, right? Expectation is less than, so evaluate the expectation of log of some p times q over p, right? That's just the statement of Jensen's inequality applied to this. Conveniently, the p's cancel out, right? Good. What's the sum of q? Yep. What's the log of 1? Notice, by the way, that I happily went to log base of e. Not that it changes this in any way. Okay, so what is this equal to? 0. Good. This is minus the Gale divergence, right? Because it was minus that, which just flips the inequality, right? So KL is greater than or equal to 0. Okay. Good. That gives an equality. Okay. Let's say, let's give you some more examples of information theory. All the time, probably a bazillion times in your life, you're working on some statistics or machine learning problem, you try to optimize some p on q theta. Okay. What do we call this? Particularly if p is an empirical distribution, meaning it's a bunch of examples with a kind of 1 over n. What do we call this? You've optimized this a bazillion times in your life. You've done any statistics or machine learning problem. If I write it in the empirical distribution, maybe you'll be happier. Okay? I'm going to write it as sum 1 over n log q theta. Theta is some set of parameters of a probability distribution q. Right? So if you like, q is a neural network. Okay, that's parameters theta. And I'm optimizing sum over data points of log q theta of those data points. What do we call that? We don't usually, but that is correct. What do we usually call that? I'm maximizing the, or log likelihood. Yep. Maximize the log likelihood. We do this all the time. In light of, notice that these two things are the same, right? This is almost the same. This is just the empirical estimate of this p of x if I get a bunch of data points. Okay? Meaning this thing will converge to this thing. Okay, as the number of data points becomes large. Okay, so what is maximum likelihood or maximum log likelihood actually doing? If I think about it in terms of information theory, you can think about it as what it's actually trying to do is it's trying to find a probability distribution so that if you use that probability distribution to encode the examples the world was giving you, it would be really compact. Okay, so it's basically saying, find me some model of the world for which the events that are coming to me are very compact to represent. Okay, so there's this very deep connection that I think we'll see again and again, which is learning is basically compression. What you're doing when you're learning things is you're compressing them. We're trying to find a probability distribution that makes the examples from the world look as small as possible. Okay, so maximum likelihood is not usually derived this way, but it is an information theoretic algorithm. It is trying to compress data as well as it can. Okay, so you can think of it as all the ways we described about it. Finding theta that best compresses the x's. You can think about it as maximizing the likelihood, and you can think about it as minimizing the KL divergence between the way real world data is generated and our model Q. All of these things are equivalent.
In the case of a policy or neural network, how do you compare this to compression?
How do you what?
Compare it to compression. Do you mean that the samples it generates need to be a narrow distribution of the real world? Like, I don't think I'm completely following the compression analogy.
Good. So I'm building a probability distribution. That's the parameters. Right? I'm going to build that probability distribution. What maximum likelihood wants to do is it wants to build a probability distribution so that if you use this Q to encode information, you would end up with a very short description of the data that's being sent. Right? That's, again, if I find the thing that minimizes the cross entropy, that's what I'm doing, right? I'm finding the code which best encodes things out in the world. You never actually compute the code, right? You skip the step of like building the code, but you basically have found a model that makes it so that it would be really compact to encode. Does that make sense? That's the relationship. You could actually use a model to encode data. Right? You can actually use, if you have any statistical model, you can use that statistical model to compress data. So if you have a transformer, you can take the transformer's estimates of probabilities and use it to compress Wikipedia to much, much smaller than a naive compression. If you use GZIP or something like that. Okay. Are we out of time?
No.
Okay, good. There seem to be people milling. Okay, good. Let's see. The point I wanted to make, but it may be relatively minor, it may not bother you. So maybe we'll do it very briefly. What? Don't use that. I'm going to skip the coin there. Okay. Now we're going to look at maximizing entropy. But I'm not going to give you enough information to nail down that probability distribution. Okay? I'm going to give you some limited amount of information. Okay? But I'm not going to tell you enough that you actually could just tell me the probability of every element. Okay? So let's say, for instance, why would I have to give you a probability distribution? There's a lot of reasons why I have to give you a probability distribution. You may need to make a bet on something. Okay? A really simple example is, again, you may need to encode information. Okay, so I'm going to give you some information about events that are going to happen in the world, but not complete information about what probabilities are assigned to each one. You're going to have to encode data, right? You're going to have to compress data, either to send it as messages to somebody else across the wire, or just to store it on disk. Okay, and you're going to need to write a code for that. How do you write a code for that? Well, the way you write a code is you write down a probability distribution, and then you do this conversion of turning the probability distribution into codes, right? Where the code lengths are in proportion to those probabilities, or log the probabilities of the lengths. Okay? So this is a very common problem where I give you partial information, and you need to produce a probability distribution, or equivalently, you need to produce a code. Right? So basically, there's a kind of a one-to-one relationship between probability distributions and codes. Okay. At least efficient codes. How about that? So let's give a very concrete example. I am going to roll a die. Okay. Maybe I'll make it a 8-sided die right now, just so that it's power 2, but for no other reason than that. But it doesn't actually matter. And I'm going to tell you no information other than I'm going to roll a die. Okay. What code should you assign to be efficient with that die? Efficiently code original die. So you get something that's going to give you a number between 1 and 8. Okay. What should you do?
Is it just uniform code?
Meaning what?
Well, so I guess there's two options. First is that you start with just the 0, just what you have now, but before when you expand it.
But say again.
So one of the options is to just have 3 digits for each option.
Sure.
So this is probably why I wanted to make it 8. But you could also skip some digits, I guess, if you stick to the property of seeing the whole message from the first digit or the second digits.
Oh, you mean the instantaneously decodable
Yes.
thing? Don't worry about that. For this discussion, don't worry about the instantaneously decodable.
Then you could also use the 0, 1, or 1 or 2 digits options.
Right. Maybe, so on and so forth. If I do that, what probability distribution am I actually effectively assigning? How would I have generated this code from a probability distribution? Uniform. Right. Okay. I definitely shouldn't there's no reason to put low probability on some particular element, right? There's nothing special about 4 that I should assign it low probability, or equivalently make it a long code, right? Intuitively, what would happen if I said 4 was improbable and I gave it a long code length in an effort to make my code on average shorter? What could happen? What's the worst case scenario?
On average, you will have longer codes.
Right. So if it turns out that the true distribution of symbols thinks 4 is very common, and you assign 4 some really, really long code, or equivalently, you said the probability of this was really small, right? 2 to the minus large number, right, is the probability of this. Then there exists a distribution of die rolls where this happens all the time, and you end up being super inefficient in how you do it. Okay, so in fact, the minimax optimal thing, the thing that is the shortest code in the worst case, meaning the worst case probability distribution sends you symbols, and you have to encode it using your probability distribution or your code, is for you to assign a uniform to each of these things. Does that make sense? Okay, so minimax optimal code. Is the code that's derived from a uniform distribution. Okay. Make sense?
Would you explain what minimax mean?
Yep. So I'm worried about minimizing the average code length, how much I'm going to have to store on disk. So just think about the space I'm going to store on disk. So I'm going to try to minimize the average code length with respect to the worst case distribution of things that could send me symbols. Okay. So there's an adversary who's going to pick a distribution to send me symbols from. Okay. And I'm going to pick a code so that I encode information, store it on disk, or send it across a wire, or whatever, so that the number of bits I have to send, on average, is as small as possible. So I'm trying to minimize the number of things I have to encode. The adversary is trying to pick a distribution so that I am as inefficient as possible. Okay? Or equivalently, I want to be robust to bad distributions. Okay? And then the claim is, if I just tell you I got a die and it's got 8 sides, what you better do is you better make them all equally probable, and you better encode it as they're all equally probable. Like this, like assign 0, 0, 0, 0, 0, 1, 0, 1, 0, so on and so forth. What you shouldn't do is prefer some to others. Because then what the adversary will do is just put mass on the things that you disprefer. Okay. Does that make sense? Okay. The additional piece of information that makes maximum entropy, so that is why you might think maximum entropy is a reasonable thing to do. Usually you have some information. You don't just know it's an 8-sided die. You have some additional information. So the simplest thing I can think, I'm going to do 6-sided die now because it breaks my head thinking 8-sided die. I'm going to think of a 6-sided die from now on in this discussion. Okay, is I'm going to give you moment constraints or expectation constraints. I'm going to give you some averages that I know about the distribution. Okay. Why? Because it turns out averages are things that I can measure very easily. I can measure average properties of the world often very easily. Just by looking at a bunch of samples, I can compute sample averages of that thing and figure out averages. Okay, so for the die roll, I might know the expectation of f of x equals 3.5 y. Okay, the function f just assigns to each side of the die the number of dots that appear on it. Okay, meaning all I'm doing is just, you can even think about it as no f at all. All I'm saying is that the die has 6 sides. What I'm going to do is compute the average number of dots that appear. Okay? If the die were fair, what would the average number of dots be? It was actually uniform. 3.5. Yep. Yeah, because it's 1 and 6, right? 2 and 5. Okay. And then we're going to divide that by 2 because I paired it up. So it's going to be 3.5. Okay. Good. So I know that this die is biased in some way. I have one piece of information about it, which I know is biased. What should I do to compute a probability distribution? Let's say because I want to encode information about outcomes.
It's not entirely clear if, like, say 6 is super likely and 5 really unlikely. So maybe just a complete pair bias towards the higher numbers.
Right. Right. So there's all kinds of probability distributions I can assign, right? So one thing I could do is I could assign all the probability mass to 4 and 5 and make it 50% 4 and 50% 5. That would meet this constraint. Do I think that's a good idea? Why is it a bad idea?
Because 6 and 1 can be like that. The skew is because of 6, and so yeah.
And it's just reducing coverage.
I've reduced the coverage, and in fact, if the true distribution has the property that it ever generates a 1 or a 6, for instance, or in fact a 2 or 3, I guess, right? Then I will have infinitely long codes, right? That's not good. I will be infinitely surprised if I ever see a 1 or a 6. Okay, so I don't want that. Okay. You hinted at the form of the answer, right? Which is the form is that it seems like it should just be biased a little bit towards the higher numbers, right? Intuitively, what might I try to do?
It lies with respect to Q, the maximal with respect to P of the entropy, the cost entropy of Q and P.
Yes, this is the adversarial depiction of the game. We're not actually going to solve that version of the game right here. I'm going to tell you what the answer is to that game. And in fact, the solution that I'm going to tell you actually is optimal for a whole bunch of different problems. Okay, one is this minimax game we just described. You just described the game. Okay, but the intuitive thing is we're going to maximize the entropy. Subject to the information I have about P, which I only have a couple things I know about P. Well, first I know P is probability distribution. Okay, I'll use delta to mean the space of probability distributions, meaning it's sums to 1 and every element is greater than 0. The other thing I know is that the expectation under P of some function, in this case a function that just looks at how many dots there are on each side, is equal to 4.5. Okay. It turns out it is non-trivial, but not that hard to actually prove that this is the solution to the mini-max problem I described. There's an adversary who's going to pick the distribution Q to generate things from, and if you don't encode this way, they will be able to make you pay more loss than if you did encode this way. Okay. There's a bunch of other justifications for this problem too. One is that if you think about entropy as the amount of information in something, if you didn't pick this distribution, you like added information that wasn't in the problem. Okay. Like you added stuff that just wasn't there. Right. Okay. That's the kind of other intuitive justification. There's a third one that I can't remember. Oh, we'll talk about it later, which is if you think about the space of probability distributions, and you kind of chopped it up into little blocks of equal size, and you asked all the probability distributions that almost meet this constraint, they are very close to the one of maximizing the entropy, as it turns out. So it's like if you kind of count them, most of the probability distributions end up being very close to maximizing. Okay, so it turns out there's a whole series of justifications. Okay, so what's nice about this problem? A variety of things are nice about this problem. Yeah.
Is this the same distribution as the one that's closest to uniform in KL that also has the expectation?
Yes. Why? Because, right, so the question was, is this the same as in KL of, the order matters here, right? In particular, min KL P to be uniform. It'll be in that order, okay? Subject to EP F equals 4.5. Okay, why is this clearly true?
Because the P log P term in KL does not matter. I mean, if we expand KL, we get a P log P term, which doesn't matter in the minimization.
You got it right here. Okay, so this is sum P log n right? This is actually the term that's going to matter.
Yeah, the other term doesn't
The
matter.
other term, the sum P log 1 over n, is, well, remember that I can pull up the log 1 over n because it's just a constant, right? Just a number. Okay? And then sum P is just 1. This is a weird thing to say, but every time I say sum P, I when I was years ago, read my children the book Charlotte's Web. There's a part where he says some pig repeatedly, some pig. I just hear some pig every time I say some P. Anyway, neither here nor there. Does that make sense? So there's an extra term. That part doesn't make sense. But just imagine that I'm thinking of a pig every time I say some P. Okay, that's some P. Some P log 1 over n is just a constant for the purposes of the optimization, right? It's because some P is always 1, right? Okay. So these problems are therefore exactly the same. They just differ by a constant in the minimization. Okay. So you can think of maximizing the entropy as finding the distribution, which is this kind of mini-max optimal. You can think of it as finding the thing that's closest to the uniform distribution, subject to has to make that constraint. Any of these things are kind of appropriate ways to think about it. Okay, what's nice about this optimization problem? We'll generalize this later, by the way, to make this not the uniform. Right? We're going to use this a whole bunch where we do actually this problem, but with a prior, when we already have information about a problem, we'll instead of solving this problem, we'll solve this problem. They're almost identical, so we'll focus on this one for right now. What's nice about this optimization problem? It's very attractive. Convex. It is a convex optimization problem. We're maximizing, it's actually concave, right? It doesn't matter, we can flip it upside down. We can minimize minus. Okay. The probability distribution is a convex set. Okay. It is a bunch of inequalities, linear inequalities. P's got to be greater than or equal to 0. and a linear equality, which is the sum of these has got to be 1. That's a convex set. It's got a concave, but we're maximizing. So if you made it min of minus h, it'd be a convex optimization. Okay, so we can efficiently find the solution to this problem directly. We could just optimize these p's directly. We could use your favorite optimizer, maybe gradient descent that you project onto the squares. Turns out there's an even more efficient way to solve this problem. Okay, and it's insightful to go through because it's going to tell you the general form of distributions that maximize entropy. Okay, and it'll establish a kind of duality between parameters of probability distributions and moments. These kind of average constraints. Okay. So the usual way this is done, the way we solve this problem, is that the way it's presented in most books is you guess the answer, and then you prove that that answer maximizes the entropy. Okay. That is not a super insightful way to do things because it's not clear how you can ever guess that answer. Okay. So I'll show you how to derive the answer, and I'm going to assume you know the method of Lagrange multipliers, and you can remember this from your Calc 3 class. I'm going to write it up. I will vaguely try to hint to you why you should believe that this method works. Okay. But you can step through it in more detail later. Okay. So what are we going to do? We're going to maximize entropy subject to this constraint. Okay. So this is literally sum pi pi minus. Okay. In Lagrange multipliers, what we do is for each constraint on the function, and hopefully I'll get the signs right, or at least I'll make a even number of sign errors. There's a constraint, there's an important constraint in the probability distribution, which is that you must sum to 1. Okay. So I put what's called a Lagrange multiplier on that. I would say sum pi minus 1. Okay. The reason this works, okay, this is called forming the Lagrangian. The reason this works is if you take the derivative of the expression I'm going to write down with respect to gamma, it just returns the constraint that the sum of pi minus 1, if I want to optimize this with respect to gamma, had better equal 0. Okay? So at the optimum of this problem, it's actually a saddle point detail, but think about it as the optimum of this problem in terms of gamma, the constraint must hold. Okay. There's one other constraint, which is what?
The expectation.
Some p of f equals 4.5, right? I'm going to make it minus constant, so I don't have to just write down 4.5 all the time. Okay. It won't change the answers. Okay. We call this thing Lagrangian. I just told you if you take the derivative of Lagrangian with respect to lambda or gamma, we're called Lagrange multipliers, I get back that at the optimum of this thing, the constraint must hold. Okay. So what I'm going to do is I'm going to take the derivative with respect to the other variable, the p variables. How many p variables are there?
And
We're in the alphabet, so 6 in this case. Okay. So there's 6 optimization variables in this case, right? And then these 2 Lagrange multipliers that enforce constraints. Okay. So somebody help me take dl dpi. And by that I mean the probability of one particular variable, one particular alphabet. Okay. So think about it as the die roll came up 3, for the sake of argument. What's the derivative of this thing with respect to pi?
We have 1 minute to derive that.
Yeah, we're not going to get it right now, but we'll come back to this next time. Okay, and we'll compute this. And what we're going to show you where we're going. What we're going to do is we're going to get the optimal form of pi. Okay, we will actually get the maximum entropy distribution, and it will end up being in terms of one variable, lambda. So we'll turn a problem which had number of symbols, free variables, into a problem which has number of moments, in this case, one variable. Okay? That's going to be the trick. And then we have to do our optimization in just one variable in this case. Okay? This is really useful when the number of possible outcomes is infinite. Right? Then the probability distribution, then optimizing the probability distribution, like for instance, if we make a continuous space of probability distribution, right? Then we end up with an infinite number of variables in one regime. In the related problem, this dual problem, we end up with just the number of moments variables. Okay, we'll do that next time. We'll maximize the entropy.